Hello, here again we are going to speak today about the meaning of inverse functions. Now inverse functions occur often in mathematics because for example when you say for example the sine function, for example, use for example sine 30 degrees is equal to half, for example. The opposite case would be what is the angle of which the sine is equal to half. And there are many functions in mathematics which are opposite or inverse to one another. For example, the exponential and the logarithm. Well, the exponential, for example, you raise 10 or e to a power. Whereas the logarithm, you are seeking the exponent to which, when you raise 10 to it, you get the number of which you started with. So, in fact, in mathematics, you always encounter functions and inverse functions. So, in this lecture, we are going to speak about these functions and expose them in detail. Now, inverse functions. First of all, we shall speak of the existence. When does an inverse function exist? Then, how to obtain inverse functions. And then later, how to graph inverse functions. And finally, we shall speak of the most important inverse function, like the logarithm or the inverse trigonometric functions, and so on. And we give some examples. Now, the existence of the inverse, when does an inverse function exist? First of all, I'd like to tell you that on your calculator, there is a button called shift. And the operation that does this button do is that it calculates the inverse function. For example, when you have square, for example, you want to square 3. So you feed in 3, and then you push the button x squared to get 9. But when you want the inverse of this, you feed in 9, shift operation, and you again push the button x squared to get the square root of 9, which is 3. So the shift button here represents the inverse operation of what you do at the very beginning. So now the existence of the inverse function is the following. When does, as I said, an inverse function exists? Now, suppose you start by 7. So 7, the square of 7 is equal to 49. So the inverse operation, the inverse question, what is the square root of 49, which is 7 on your calculator? So really, this is not really the exact question, because calculator, they know their way. But we have to understand it too. So the question is not what is the square of 7 to give 49, and the contrary question, the opposite, what is the square root of 49 to give 7. But the question is, the square of 7 is 49, but what are the opposite question is that what are the numbers that when they are squared, they yield 49. They are not only 7, but you may have 7 and minus 7. And this is actually is not to be accepted. Why? Because we know that for a function to exist, then it has to map one value in the domain of the function into one value in the range of the function. So here 7 gives 49. But the opposite question, which is f minus 1, we denoted by f minus 1, the question is, what are the values? 1 squared give 49. So you have here, you must either end up with 7 or you end up with minus 7. You can't have both, because the arrow must end up, as we said before in our third lecture, must end up in one unique value in the range of f minus 1 here in this case. So either you choose, you have two possibilities. Either you say that 49 here end up with 7, give 7 as the operation f minus 1, or you choose the other one. 49 here gives minus 7. So actually these are the two branches that you have to choose between in order to obtain your inverse function. And calculators, for example, choose the first option. So here again, here is y, this is the same example, y is equal to x squared. So either you choose x1, this is the first function, is equal to square root of y. You solve x as subject. Either you have x1 is equal to square root of y, or x2 is equal to minus square root of y. So each of them could be an inverse function to the original function y is equal to x squared. But it depends on the domain of x squared here. Either you choose the values of x greater or equal to 0, or the values of x less than equal to 0. It's up to you to choose the inverse function to this particular function. But as an original function y is equal to x squared, in fact, such function has no inverse because because although for each x there is a unique y, but for one value of y it yields two values of x, and therefore we call this function an improper function to obtain an inverse function out of it. So the reason why this function we cannot obtain an inverse function out of it is that the horizontal line in which we draw met the graph in two values, x1 and x2. And here as well, this function here, one horizontal line gives three values of x, of which they all have the same value of y. So an inverse operation then of y gives you three values of x. So this function also has no inverse according to our definition of inverse function. So in order that an inverse function then to exist, the original function has to be, it's called injective. Injective meaning that for each x there is an y, but also for each y there is one value of x. For example, here there are two x's, and therefore y is equal to x squared cannot have an inverse function. Either you choose the branch for which x is positive or the one for which x is negative. Whereas here, this is a monotonic increasing function, which is x cubed. This has an inverse. Why? Because if we draw any horizontal line, it will meet the graph into only one point. We call this kind of functions injective functions. So an injective function is a function in which you can calculate the inverse. Usually, the condition under which a function is injective, there are many ways of saying that this function is injective. The best thing is to draw a horizontal line and see where does it meet. But if the function is monotonic increasing or monotonic decreasing, then we are sure this is sufficient to be injective. Of course, this is it's not necessary, it's only sufficient, but it's also necessary if the function is continuous. In other words, if you emit continuous function, then all you have to do is that to check whether it's increasing all the time or decreasing all the time, and therefore it's an injective function. So the first condition, the function has to be injective in order to have an inverse. The other thing too, the function, if for example you want to obtain the inverse of y squared, in the domain of the inverse, you cannot choose a value here, for example, for y. Because, for example, if you choose y is equal to -1, can -1 is equal to x squared? You can't have an x such that x squared is equal to -1. Usually, we have to stick in the domain of f minus 1, we have to stick to those values that lie in the range of f. In order that the function has an inverse function. But then we know very well that f maps from the domain of the function till the codomain of f. And f minus 1 here, since it maps the values from the range of f till the domain of f, which is the range of f minus 1, then here directly, since this is the opposite of this one, so we must have that the range of f is equal to codomain of f. In other words, we have to restrict the codomain of f to be equal to the range. In other words, we restrict the range of f to cover all the codomain of f. In other words, f is an onto function, or as we said before, a surjective function. So now f is injective, and now f is also surjective. We call the function when it is injective and both surjective, we call it a bijective function. But this restriction of surjectivity is not needed, because we can always restrict the codomain of the function to be the range of f, and therefore injectivity or injective functions are, when we check the injective criteria, it's enough as a condition to find an inverse function. So all you have to do in order to find the inverse of a function, you have to check first whether the function is injective. And to be injective, if it is continuous, then you check that whether it is increasing all the time or decreasing all the time. So here, we come up to this conclusion then, that the domain of f minus 1 is equal to the range of f, whereas the range of f minus 1 is equal to the domain of f. So suppose now we have a function and we calculated the inverse. So since we calculated the inverse, then if you go back to the back slide here, since we calculated the inverse, we can move actually the function f, make us move from x till the range of f, a point y in the range of f. Of course, if we do a composite operation of f minus 1 of f, suppose this is the inner function, this is the outer function. In other words, f minus 1 f of x, what do we obtain? F minus 1 f of x is equal to xy, because we operate from x till y and then from y again to x. So f minus 1 of what? Of y, which is f of x, must be equal to x. Or you may say that you may start from y. So f minus 1, you have here f of what? Of f minus 1 of y. You start from y to get x, and then from x to y. So f minus 1 of y to get x, and then f of f minus 1 must be equal to y. So what we actually have now obtained is that f minus 1 of f of x must be equal to x for all x lying in the domain of f, and f minus 1 of y must be equal to y for all y lies in the range of f. And this is the way, this is a test to know whether the function f minus 1, which you obtain, is really an inverse function of the original function f. So now how can we obtain inverse functions? First of all, we have to make sure that f is 1 to 1. 1 to 1 means injective function. In other words, one value of the x gives one value of y, and the opposite also is true. One value of y gives one value of x. And this is easy. If the function is monotonically increasing or decreasing, then it's sufficient condition for that the function is injective. After we do that, we solve y is equal f of x in order to make x a subject. The meaning of English, usually they say x a subject. In other words, they solve x for y. For example, y is equal to x squared, then x is equal to square root of y or minus square root of y. So, and after they do this, with this you have end up, this is finished, because the operation, we said before that the operation is not the variables x and y, but the inverse operation. This is the function f, the original operation, and this is the inverse operation. So here it's finished. Here we calculated the inverse function, but we usually, what we like most of the time is that we like the independent variable to be on the right hand side and the dependent variable on the left hand side. We like this to be x and this to be y. So we do a final step is that we interchange the variables x instead of y. So whereas here we finished the problem, and yet it's nice to put it in this form. For example, here, y is equal to x cubed. This is the original operation. What is the inverse of this operation? Of course, y to the power 1/3. So here we have the graph y is equal to x cubed. And if we move from a particular value of a, using the operation f, we end up with a cubed. But on the contrary, if we move from a certain b, using the operation f minus 1, we must end up with b to the power 1/3. So actually what you do, when you move from x to y, you move with f, and when you move from y to x, you operate using f minus 1. So, but here you realize something. Here is the function f, and here is the function f minus 1. It's not necessary to use the same variables. The important thing here, you take the cube of x, and here you take this cubic root of y. So these are opposite to one another. But here the only drawback here is that you use the same curve. You use the same curve to obtain f and f minus 1. And it's better most of the time to have the independent variable on the x-axis, on the horizontal axis, and the dependent variable on the vertical axis. So what we do, we replace the variable. Instead of writing x is equal to y to the power 3rd, we write y is equal to x to the power 3rd. For example, here, for example, we have y is equal to x squared. Y is equal to x squared, but we showed the branch in which x is negative. So what is the opposite of this? We solve this. The first step is to check that that the function is that is 1 to 1. It is, yes, because it is monotonically decreasing. Therefore, it's injective. So it has an inverse. The inverse is what? We make x as subject. That's the second step. So you get x is equal to either square root of y or minus square root of y. But then, since x is negative, we restrict ourselves to the minus square root of y. So here now it's finished. Now we got the inverse function. But it would be nicer if we let the independent variable, in this case y, to be x, and x is y. So we change y into square root of minus x, and we draw the inverse function as this. This is the inverse function, y is equal to minus square root of x. Here we realize something. Here the domain of the original function is x less than 0. So it must be equal to the range of the inverse function. Yes, the inverse function, the range is y is less, x is less than or equal to 0. Whereas here the range of the original function, x greater than 0. So this must be the domain of the inverse function, x is greater or equal to 0. So the range of the first one is the domain of the second, and vice versa. And here is exactly what we did. You have here y is equal to x squared with x negative. Here we have y is equal to minus square root of x with x positive. The domain of this one is that, and the range of this one is also negative values of x. Whereas the range of this one are positive, and the domain of this one, those values of x are positive. And this is the inverse function, y is equal to minus square root of x for all x greater than equal to 0. We notice also something, that the point, since the point minus 7 and 49 lies on the graph of the original function, so on the contrary, on the inverse function, the point 49 and minus 7 are the one to be found on the graph of the inverse function. So here it says something, that the point P of A and B on the graph of f must coincide with the point P of B and A on the graph of the inverse function. So there must be a symmetry. Yes, both curves or both graphs must be symmetric with the line y is equal to x all the time. The straight line was equal to x. And this is one way of checking whether you are correcting, whether you are correctly found the inverse function, is that you find the graph and the opposite, or which is the graph of the inverse function. Both of them must be symmetric to the line y is equal to x. Again, here is y is equal to x cubed. Y is equal to x cubed, then the opposite, the inverse function, you solve x in terms of y, so you get x y power to the third, and then you replace the variable, so you get y is equal to x to the power third. Here, both the function and the inverse function, both of them have domain R and range R. And you see both of them are symmetric with the line y is equal to x. So here, as we said, we notice the symmetry around the line y is equal to x. In other words, the point P of A and B on the graph of f corresponds all the time to the point B of A, P of B and A on the graph of f minus 1. This is a problem. Find the inverse function of this function here, square root of 5x plus 8. So this is the original function here, and you see directly that the domain of this function for those values of x that makes 5x plus 8 under square root positive, x must start from minus 8 over 5. So now the domain of the original function are the closed interval from minus 8 over 5 till infinity, starting from here. Now you solve x in terms of y, and you get this one here. Easily. When you solve this, of course, you better interchange. You interchange x by y, and you get this. Here you directly notice that the range of this function starts from minus 8 over 5. This point is minus 8 over 5 and 0, and this point is 0 and minus 8 over 5, because they coincide to each other. So the range of this function must be equal to the original, the domain of the original. So the range of the inverse functions from minus 8 over 5 to infinity, whereas the domain of the inverse function is equal to the range of the original function from 0 to infinity. Now, if we want to check whether what you obtain is really your inverse function, it's easy. As you said before, here what you get is what? Here what you get is f minus 1, because you started with 1 over 5. This is the inverse function, 1 over 5 of x squared minus 8. So you substitute, you get a composition between f minus 1 and f. And this is what you get here. This is f minus 1, f of x must be equal to x for all x lying in the domain of the original function. Whereas here is what? Here f minus 1, because the square root 5x plus 8. So 5 times f minus 1, the composition between f and f minus 1 of y must be equal to y for all y lying in the range of f. And the range of f are those y are positive. And since they are correct, these coincide, because of course when you take the square root of this, what you get here? What you get, this cancelled out and this cancelled with this, 8 minus 8, you get square root of y squared, which is mod y, and mod y is equal to y since y is positive, so you get a correct answer, and therefore your inverse function is that. Now, how do we graph inverse function? This is one way. How do we graph them? Now there is one simple way of doing this. You always start with the graph of f. This is the first step. You have 3 steps to do. This is, for example, this is the original, the last example which we explained. Now, this is the graph of f. What you do is you do a counterclockwise rotation of the graph of f to obtain this one here. So this is the second step. When you do this, after that, this is the second step. You put a mirror on the y-axis to obtain this graph here. To make it more clear, suppose, for example, this is the same example here. This is the same example. Now, this is the example above. This is what we started with. This example, you do a clockwise direction, like this, to obtain this one. Then the last step is what? You put a mirror here. When you put a mirror here, you see this one here. So this is the inverse function. So this is the original function, and this is the inverse function. And if you plot them together, what you get, as a matter of fact, here is you get, this is now your inverse function. This is the original function, which was like that. And this is the inverse function. And you see that both of them, if you draw a line here, both of them are symmetric with the line y is equal to x. You get like this. This is the line, and you get both must be symmetric. Again, suppose, for example, that you have here, this is, you investigate, for example, the curve y is equal to 1 over x plus 1. Now, this is the original function. The original function, now the domain is what? Is r except minus 1. And the range is what? Is r except 0. This is the original function. What do? You rotate anti-clockwise like this, 90 degrees. And then what you do, you put an arrow here. You put a mirror here on the y-axis. When you put a mirror here, what you get? You get this one here. So now, the domain of this function is the range of the original function, which is r except 0. Whereas the range of this function is the domain of the original function, which is r except minus 1. So this is the original function here, and this is the inverse function here. And in fact, you can put them together to obtain this one here. This is the original function which you started with, 1 over x plus 1, which exclude minus 1 from its domain, this one here. And the intermittent line here, this is your inverse function, the one which is not complete here. And actually, both of them must be symmetric around the line y equal to 1 here, like this. This line here, you find here, the line must pass, the intersection of these two curves here must pass by the origin, and both must be symmetric around the line y is equal to x. Now we can also show it using an applet here. What we have here, for example, you have an applet here. This is the curve y is equal e to the power x. Now, what you do first, you rotate, you rotate your function 90 degrees to get this one here, the blue one. And then after that, you put a mirror to obtain this one. Here, this is the original function, and this is the inverse function. This is an exponential, and this is a logarithm. You may also, for example, have the curve y is equal to x cubed. This is x cubed. What is the inverse of x cubed? It's x to the power third. So you rotate anti-clockwise. You get this one. And then you put a mirror. You get this one. Here, the original function, x cubed, and this is the inverse function, x to the power 1/3. And both have a range and domain r. Finally, for example, this is a cosine function. Now, a cosine function, of course, a cosine function cannot have an inverse y because cosine function is periodic. So it's not an injective function because for a value of 1, for example, you have a 0, you have 2 pi, etc. So this is not an injective function. For each value of y, there are an infinite number of values of x. So you have to choose a period or an interval in each of the function is monotonic, increasing or decreasing, like this one here, to be injective. In other words, for a value of y corresponds only value of x. So we chose only the period in which you have from 0 to pi. From 0 to pi, the function here is injective function. So what you do, you want the inverse. You rotate anti-clockwise, 90 degrees. You got this one. And then you put a mirror on the y-axis to get this function. You notice here, this is the original function, and this is the inverse function, and both of them must be symmetric around the line y is equal to x. Now, one major applications of the inverse function, usually students, they find an easy way to find the domain of the function. But for the range of the function, it is difficult. So since now we know that the range of the inverse is equal to domain of the original function, and the range of the function and the domain of the inverse function is equal to the range of the original function, so it's easy now. If you want to calculate the range of the original function, all what we do is to obtain the domain of the inverse function. So suppose, for example, you have here, as I said, the range of f coincides with the domain of f minus 1. So once we calculate the domain of f minus 1, this coincides with the range of the original function which we seek to calculate. Now suppose, for example, you have a function of this one, y is equal to 2 divided by x squared plus 8, and they ask you to calculate the range of this function. Now the range is easy here because R, the domain is R. But if we take the domain of R, and this is the original function here, this is not an injective function because it's monotonic increasing than monotonic decreasing. So it's not injective. So you have to restrict ourselves to a region in which the function is injective. So for example, we restrict ourselves to the value of x, which is x greater or equal to 0. In other words, we shall find the inverse of this branch here, starting from 0 to infinity, and this is the monotonic decreasing, and therefore it has an inverse. Now, what is the inverse of this function? It's easy. We can solve x in terms of y. Yx squared plus 8y is equal to 2. So x is equal to square root of 2 minus 8y divided by y. Now, y is positive from the first equation here. So in order to obtain the domain of the inverse function, which we seek because this is equal to the range of the original function, all we have to do, we have to make sure that what is under the square root is positive. Now, y is positive, as we said before. So what remains, that 2 minus 8y must be positive. In other words, y must be less than a quarter, 2 over 8. So now we have calculated the range, the domain of this inverse function. So it ranges from y greater than 0 because we cannot divide by 0, until 1 over 4. What this means, this is equal to the range of f, to the domain of f minus 1. But since the range of f is equal to the domain of minus 1, so what in fact we have done is that we have calculated the range of the original function. So one way of calculating range of functions is via calculating the domain of the inverse function. Now, we have to to expose ourselves to the inverse of some important function, like, for example, the inverse of the exponential function. Now, the exponential functions, what is the inverse of the exponential function? It's the logarithmic function. So log to the base a of x is the opposite of a to the power, or the inverse function of a to the power x. There we calculate a to the power x, and here we found the exponent. When raised a to it, you obtain x. Of course, we exclude a is not equal to 1. Why? Because a to the power x, when a is equal to 1, is not an injective function because it's straight line all through, so it has no inverse. But otherwise, if a is not equal to 1, so you get the logarithmic function. And here it gives you different values of here, for example, a to the 0.1 coincides to 10 to the minus x, because 0.1 to the x, so this corresponds to 10 to the minus x, and the others are e to the x, 10 to the x, etc. And this you got different values of logarithmic functions coinciding with the base 2 or 10 or e. Now, there, e to the power x, the range of which are those values, those positive values of x. So this must coincide with the domain of the inverse function. So the logarithm of x, the domain of which are the range of the exponential, which are all x are greater or equal to 0. Whereas the range of this function is r. Why? Because this coincides with the domain of the original function, which is the domain of the exponential, which is also r. So now we have here is the exponential function, and here is the logarithmic function. And you see that both of them are symmetric with the line y is equal to x. So the point 0 and 1 on the graph of e to the power x coincide to the point 1 and 0 on the graph of logarithm x. And the domain of this is equal to the range of the other one. And again, here the composition between the two. For example, here you have what? Here you have f of f minus 1 of y, of x or of y, doesn't matter. The variables are not important. It's the operation itself. Here you have what? Here you have f minus 1, because this is the inverse of the exponential. F minus 1, f of x is equal to x for all x lying in the domain of e to the x, which is r. Whereas here you have what? You have f minus 1 of x is equal to x for all x lying in the range of the original function, which is all values of x greater than 0. So f minus 1 f of x is equal to x, and f minus 1 of y is equal to y, or f minus 1 of x is equal to x for all values of x lying in the range of the function f, which is all values of x which are positive. Now, these are properties of logarithm, and all of you know them. Logarithm AB, for example, logarithm A plus logarithm B, and all of this, you can find them in any pre-calculus book. Now, these are the trigonometric functions. We've chosen only a few of them. For example, sine x. You seek, for example, the sine of 30 degrees is equal to 1/2. What is the angle of which, the sine of which is equal to half? It's equal to 30 degrees. So now here is the original function sine. We cannot take all the sine graph because it's not injective. We restrict ourselves from in the interval from minus pi by 2 till pi by 2. This is the domain, and the range from minus 1 to 1. So the inverse must be the contrary. The domain from minus 1 to 1, and the range from minus pi by 2 till pi by 2. And you got the inverse function. Both of them, if you draw them together, you will find them symmetric around the line y is equal to x. Finally, you have hyperbolic functions. Now, we said before that hyperbolic function like sine hyperbolic x, this is the representation or the definition of sine hyperbolic x. Now, we see here that hyperbolic functions are based on exponential functions. So we should, in fact, if we are by logic, that the inverse of the hyperbolic function must be based on the inverse function of the exponential, which is the logarithm. In other words, if we seek to determine the inverse function of the sine hyperbolic x, it must be based on the logarithmic function of x. And this is true. All you have to do, you can solve this, y is equal to half e to the x minus e to the minus x. You can solve them and obtain x in terms of y easily. Here, this is a second degree in e to the power x. You multiply this equation by e to the x to obtain e to the xy is equal to half e to the twice x minus 1. And you solve in terms of e to the x as subject, you obtain e to the power x in terms of y, and then you take the logarithm, and you end up with this form here. This is the original function. Twice y is equal to the e to the power x minus e to the power minus x. You multiply by e to the x. You got a second degree equation in e to the x, whose solution, here the solution, and then you represent x in terms of y. And of course, this is the inverse function, the logarithmic function. Of course, you may replace, if you want, you may replace x by y if you wish. But this is the inverse function of the hyperbolic function. And like this, we actually have come up with the end of our lecture because we expose now inverse functions. We exposed the exponential functions and the anti-exponential, which is logarithmic functions. We said that for a function to have an inverse, it must be injective, or it must, in which case you can check whether it's monotonic increasing or monotonic decreasing, and this is a sufficient condition. This is another example here. It tells you, for example, this is the function f, and you want to prove that this is the inverse of f. Now, this function f, e to the power x, square root of x is always increasing, so e to the power x is increasing. The logarithm of something which is increasing, this is a composite function, must be increasing, so this is a monotonic increasing function. Since it is a monotonic increasing function, so therefore it is injective, and therefore it has an inverse. So how can we calculate the inverse of such function? It tells you here this is the result, but you can do it. All you have to do is from here, for example, you can solve x in terms of y. You set y is equal to logarithm of e to the power x minus 1. So if y is equal to logarithm, it means what's inside the logarithm is equal to e to the power y. Like this. And then you want to solve x in terms of y. So you get e to the power x is equal to the e to the power y plus 1. So what is the value of x? Finally, you have square root of x. You take the logarithm of both sides. You have logarithm of e to the y plus 1. So now, from this, you can proceed down it. You get to obtain x. So what's the value of x? X is equal to what? To squaring the square of logarithm e to the power x plus 1. Of course, you can interchange, as I said. But it's enough to say that x is equal to logarithm e to the power y plus 1 all square. Now, this is a theorem which is nice, and it relates composite function in inverse functions. Sometimes, for example, you have a composite function of f and j, and you wish to obtain the inverse of this function. So you have two solutions, two choices. Either you calculate, it tells you, either you calculate the composition, which we done in our last lecture, and then after you do the composition, you seek to determine the inverse of this composition here. The inverse of this composition, in other words, you check first. First, for example, it is known that if J is injective and F is injective, for example, J is monotonic increasing and F is monotonic increasing, for example, then you are sure that F circular J exists. Once you do that, you calculate the composition, and then you seek to determine the inverse of this composition. This is one choice of doing this, but there is a theorem which you can use and which facilitate your task. It tells you directly that the inverse of a composition is equal to the composition of both inverses. In other words, you can calculate, if you know that G has an inverse, you can calculate the inverse of G, and you can also calculate the inverse of F. And then you can calculate the composition of the two. And actually, this is interesting. Why? Because it exists in other topics as well, not only in calculus. It exists even in matrices. If you are aware, for example, you have two matrices A and B. Matrices are arrows made of arrows like this. You have an arrows of rows and columns like this. And this you use all the time in solving equations. You must have them, take them in school. At least you have, for example, a 2 by 2. For example, 2, 1, 1, minus 1. For example, this is a matrix. You may have 1, 0, 2, 3. This is another matrix. If you multiply them together, you get AB. Well, then there is a theorem in matrices tells you that AB to the inverse of the product of two matrices is equal to the inverse of the first one times the inverse of the second one. And this is strange theorem that instead of multiplying both matrices and then finding the inverse, what you can do, you can calculate first the inverse of the second one, and then you multiply it by the inverse of the first one. And what is interesting here is that you interchange them. Well, here you start with A, then when you do the inverse, you start with B. And same thing with here. Here, what we have here, the inverse of the composition F circular J is equal to composition of the inverse, but here you realize that it's the inner function which comes into the composition. The inverse of when you calculate the composition here, you have to do the operation G first and then F. So the inner function here comes first as its inverse. So F circular J is equal to G minus 1. Composition of G minus 1 circular F minus 1. So now we come to the end of the lecture, and with this we have exposed the concept. The main important thing of this lecture is that we have exposed the concept of the inverse, and we have set the conditions under which an inverse function exists. It must be both injective and surjective, and we said that injectivity is enough because we can restrict the codomain of the function to be the range. And once you can check this by, for example, checking that the function is monotonic increasing or decreasing. This is a sufficient condition to be injective. And once you do this, then you solve x in terms of y. If you have y in terms of x, and you replace the variables, and you get the inverse function. And we saw how we do this also by graphs, by rotating the graph of the function anti-clockwise, etc. So with this, we come to the end of this lecture. I thank you for your attention, and I like to remind you again that all these lectures are uploaded to the platform of the Uninutudu Telematic University. Thank you. and again in our next lecture.